Science is all about learning how nature behaves so we can modify matter and energy to suit our needs. And humanity excels at modifying matter and energy, more so than any other creature now or ever. But before we can modify it efficiently, we have to understand it. Believe it or not, it was more challenging than you think. Consider this analogy. If you live in a two-story house, how do you get to the second floor? You probably take the stairs. Some houses, though, are outfitted with ramps instead of stairs to go from one level to the other. What's the difference between a staircase and a ramp? Both of them allow you to go up and down. The main difference, though, is that the elevations of a staircase are specific or discrete. Each step takes you to a specific new height. A ramp is different. Its height varies continuously, so that from start to end, every altitude is reached as you go up or down the ramp. Discrete versus continuous. That's the difference between a staircase and a ramp. On one, you only reach certain specific heights. On the other, every height is possible. But both do the same job. They get you up and down. How does this relate to matter and energy? Well, more than you might think. If we want to use matter and energy to our benefit, we need to know something of their nature. The better we understand them, the better we could use them. So let's see how our staircases and ramps relate to matter and energy. For one, it's pretty easy. For the other, we needed a virtual revolution in our understanding of the universe. Take a piece of aluminum foil, about 1 inch square, and cut it in half. It's still a piece of aluminum, right? Now take the half and cut it a second time. Again, it's still aluminum. Cut it in half again, and again, and again. Every time you cut it into smaller and smaller pieces, you're still holding a piece of aluminum. It's as if matter were continuous, like our ramp. Is there some point in our cutting where we have to stop? Granted, the pieces get tinier and tinier, but hypothetically, how far can we go? Well, as far as we could see, we could go on forever, right? It's pretty obvious that matter is continuous, so we should be able to cut our aluminum foil into smaller pieces forever. Of course, this isn't the case. We all know that at some point we get to the smallest piece of aluminum that can be called aluminum. It's an atom. The word atom comes from the Greek word that means indivisible, and the theory that matter is composed of atoms dates back to the 6th century BCE in India and the 5th century BCE in Greece. But that was one of several ideas about the structure of matter. Unfortunately, there was no direct evidence of matter as atoms. It wasn't until the early 1800s that enough evidence was collected to support the existence of atoms, and what we now call the modern atomic theory was announced by John Dalton in 1803. Although there was some resistance to Dalton's ideas, especially because no one had ever seen an atom, over time most people accepted that the modern atomic theory was correct, and the science of chemistry advanced significantly after that. Individual atoms were finally seen in the mid-1980s after some new technology was invented. But at this point, nobody seriously doubts the existence of atoms. The point, though, is that matter is not continuous, as was long thought. Matter is composed of discrete individual atoms. The thing is, these atoms are so tiny that matter looks like it's continuous. And for the most part, it acts like it's continuous too. But when scientists started doing careful experiments with matter in the 1800s, they found that the only way to explain their results was if matter came in discrete but tiny pieces. How small are these pieces? It would take about 100 million atoms to make a line 1 inch across. But still, matter is a staircase, not a ramp. Discrete, not continuous. Now, granted, the staircase has very tiny steps, but in most circumstances we could treat it as continuous, but it's a staircase nonetheless, only with very tiny steps. By the way, that piece of aluminum we were talking about, you'd be able to cut it in half about 30 times before you got down to a single atom of aluminum. But by the time you got to the 11th cut, your piece of aluminum would be narrower than a human hair and you'd probably drop it. Probably better start using tweezers. Let's go back to the 1800s, at least mentally. It was a century of intense exploration of matter and energy as science expanded tremendously. During the course of these explorations, though, some phenomena were discovered that couldn't be explained by the science of the time. Understand that the goal of science is to learn about and model the natural universe. Scientists do this by conducting experiments, making measurements, developing and testing hypotheses, and then rechecking things over again to confirm their results. Eventually, a model of a particular phenomenon is developed. This model is called a theory. In science, a theory is a general statement that explains a large number of observations. Good theories not only explain observations, but have the ability to predict new behaviors in different circumstances. If a model does not agree with how the universe operates, we have two choices: change the universe or change the model. Because all attempts to change the universe have failed, we're sort of stuck in this one, we're faced with changing our models. This has actually happened many times throughout the course of history. Understand, too, that when science uses the word theory, it doesn't mean hypothesis like we mean in everyday life. If you were to say, "I have a theory that Colonel Mustard committed the murder in the observatory with a lead pipe," you're really using the word theory to mean hypothesis. That's not how science uses the word theory. Scientifically, a theory is a general statement that explains a large number of observations. It's a very high standard in science to call something a theory, and it does not mean hypothesis. So in science, we have the cell theory of life, that all life is made of cells. Atomic theory of matter, that matter is composed of atoms. The theory of evolution, that life changed over long periods of time. And the theory of gravity, that all matter attracts other matter in predictable ways. These scientific theories are all well tested, have survived intense scrutiny, and are hugely successful in modeling the natural universe. That's what science means by theory. Let's talk about the rise of another important theory called quantum theory. Many of the unexplainable phenomena that scientists found in the 19th century had to do with the interaction of light and matter. For example, in 1860, German scientists Gustav Kirchhoff and Robert Bunsen invented the spectroscope. In this device, light was split into a rainbow with a prism, and then the rainbow was sent through a slit that allowed a single color of light to pass through a chemical sample. The prism was rotated so that each color passed through the sample sequentially. As light passed through the sample absorbed certain colors of light, but let other colors of light pass through unaffected. A plot of the absorption of light versus color is called a spectrum. Kirchhoff and Bunsen noted that the different elements all had different spectra, suggesting that a spectrum is a way to identify elements apart from each other. In a similar setup, a sample was heated in a flame, and the light given off by the flame was passed through a prism and displayed. In this case, the sample actually emitted only certain colors of light, but not others. The colors of light emitted were exactly the same colors that were absorbed in the original setup. Again, the specific colors emitted were characteristic of the elements in the sample. For example, sodium vapor gives off a strong yellow color that you can see in some streetlights. And the different colors of so-called neon lights are caused by different gases like argon and krypton, not just neon. The element hydrogen had a particularly simple spectrum, which made sense. Hydrogen was already known to be the simplest element. But there's a bigger question. Why? Why do elements have characteristic spectra, and why was the spectrum of hydrogen so simple and regular? Scientists could not explain this at the time. This relationship between light and matter remained a mystery. Another mystery of light involved its emission by a hot piece of matter. We all know that hot objects glow. They emit light. We even use phrases like red hot and white hot to describe hot, glowing objects. Scientists assumed that all colors of light would be given off equally because there's no reason to believe that any one color is given off preferentially. A graph of intensity versus color should therefore look like a straight line. Instead, when scientists actually measured the intensity of emitted light versus color, they found a graph that looked like a misshapen camel's hump, with some colors of light more intense than others. Clearly, there is a preference of some colors over others, but scientists couldn't explain why. Granted, there were several attempts to explain why hot objects gave off light like this, but all of them fell short. One thing to keep in mind during all this is that light was known to be a wave. Throughout history, it was argued whether light was a wave or a tiny particle. Isaac Newton favored a particle nature of light, and he was pretty influential. But he was wrong. Light is a wave. That was clearly demonstrated in 1801 by English scientist Thomas Young, who showed that light experiences constructive and destructive interference, just like water waves do. As a wave, light has certain properties. It has a wavelength, the distance between two waves, and it has a frequency, the number of waves that pass by a point every second. For any wave, including light, the velocity of the wave equals its frequency times its wavelength. And for light, that velocity is represented by the lowercase letter c. In the mid-1860s, Scottish physicist James Clerk Maxwell deduced that the speed of light in vacuum was a constant, and it's a very large constant, 186,282 miles per second. That's 7 times around the Earth every second, 1¼ seconds from here to the moon, 8 minutes and 12 seconds from the sun to the Earth. In our current theory of physical space, nothing can travel faster than a wave of light. With this in mind, scientists of the 19th century were trying to explain why light interacted with matter the way it did. But all their attempts to develop a model failed. So again, we have a choice. Change the model or change the universe. Well, we can't change the universe, so we have to change our way of thinking about the universe. And that's exactly what happened. Max Planck was a German physicist who specialized in thermodynamics, the study of energy and matter. He began studying the light intensity issue in 1894. After several failures, in late 1900, he came up with an idea that actually seemed to work. Planck considered the atoms in the glowing matter and thought of them as little oscillators wiggling back and forth with a certain frequency. Planck wondered what would happen if the energies of these little oscillators were related to the frequency of the oscillation. In modern terms, what Planck was proposing was a simple mathematical formula, E equals h nu, where E is the energy of the oscillator, the Greek letter nu is the frequency of the oscillator, and h is a proportionality constant now known as Planck's constant. When Planck made this assumption and applied it to glowing objects from a thermodynamic perspective, Planck was able to derive a mathematical formula whose plot agreed perfectly with the intensity of light given off by a glowing piece of matter. Now, everyone agreed that Planck's equation works, but there was disagreement on what Planck's assumption meant. The assumption that energy was related to frequency, that is. First of all, let's understand why this assumption was a radical idea. If we think of a wave as a simple up and down motion, then the distance between the top and the bottom of the motion is called the amplitude. Classically, the energy of a wave is related to its amplitude. A louder sound wave has a larger amplitude than a softer one. A wave in the ocean that knocks you down has a larger amplitude than a wave that just laps at your feet. Amplitude has always been an indicator of energy of a wave. Not so for these little atomic oscillators, according to Planck. Planck was proposing something completely different, that the energy of the oscillators is related to their frequency, not their amplitude. That is, the energy of the oscillators was related to the number of back and forth wiggles each second, not the amplitude of the wiggle. It was only natural that colleagues were a bit skeptical, as it went against everything they understood about the behavior of waves. Some thought that Planck's assumption and derivation were just mathematical tricks. Even Planck himself, to some extent, was a bit skeptical. He's been quoted as saying that his work was an act of despair. I was ready to sacrifice any of my previous convictions. After all, even good scientists should be skeptical, even of their own work. But it turns out that Planck was right. And who of all people should be there to help out? Only one of the most famous scientists of all time. Albert Einstein was another German physicist who, until 1905, was invisible to the scientific community. But in that year, he published a few papers on different topics, each of which rocked the physics world. One of them was on relativity, the topic for which Einstein is probably best known. But one of them involved Planck's hypothesis relating energy to frequency, not amplitude. It was related to a phenomenon called the photoelectric effect. When you shine light on a metal surface that's kept in a vacuum, under certain conditions, electrons are given off. This is called the photoelectric effect, and it's still used today to construct certain types of electronics. While straightforward, it's the trends that are unusual. If you increase the intensity of the light, more electrons are given off, but they don't come off faster with more kinetic energy. On the other hand, if you increase the frequency of the light that you use, the same number of electrons are given off, but they come off faster with more kinetic energy. Finally, below a certain frequency of light, no electrons are given off at all. The photoelectric effect was discovered by German scientist Heinrich Hertz in 1887, but he and others weren't able to explain why it occurred and why it showed such trends versus the frequency of light. In fact, the photoelectric effect and these trends in its behavior were another unexplainable phenomenon related to light that was discovered in the 19th century. Einstein proposed that it wasn't just Planck's atoms that had an energy proportional to their vibrating frequency. He proposed that the energy of light itself was related to its frequency, using the same equation that Planck proposed, E equals h nu. That is, the energy of a light wave was fixed. It was determined by its frequency, not its amplitude. Does that sound familiar? We have a word for when a quantity is fixed. We say that quantity is quantized. Light, Einstein proposed, was behaving as if it were a fixed package of energy, depending on what its frequency was. So the energy of light is quantized. What this also means, by the way, is that because different colors of visible light have different frequencies, different colors of light have different energies. Einstein then explained the photoelectric effect this way. An electron is held by a metal with a certain amount of energy, which became known as the work function of the metal. When light is shined on the metal, an electron in the metal can absorb one light wave. Any light waves having less energy than the work function will not cause the electron to be emitted. If the light has a high enough frequency, that is, a high enough energy, the electron will absorb the light, overcome the work function, and be emitted. Any leftover energy from light not used to break free will be converted into kinetic energy, or energy of motion. The higher the energy of light, that is, the higher the frequency of light, the greater the leftover energy that becomes energy of motion for the electron. A higher intensity of light means more light waves, so more electrons can be emitted, but not any faster. However, a higher frequency of light means more energetic light, so the emitted electrons come off faster. By suggesting that the energy of light was determined by its frequency, Einstein explained the photoelectric effect. His ultimate conclusion was that the energy of light is quantized. Einstein's proposal was initially looked upon skeptically by his colleagues, but eventually it took the scientific world by storm. And by eventually, I mean it took about a decade to convince most scholars that Einstein's idea was the correct model. It's crucial to understand, though, that the implications of Einstein's application of quantized energy were profound. What was initially a wild proposal, a mathematical trick by Planck to explain light from hot glowing objects, E equals h nu, became a fundamental change in our understanding of light. Einstein's ideas of light were so basic to our knowledge of not just light but the rest of the universe that he won the 1921 Nobel Prize in Physics. Not for his more famous theories of relativity, but for his revolutionary ideas on the nature of light. But let's get back to the idea of whether light is a particle or a wave. In a sense, Newton was right. Light is acting like a particle. Because light has a certain specific amount of energy depending on its frequency, light is acting like a little particle of energy. But isn't light also acting like a wave? Yes, it is. It has wave properties like frequency and wavelength. It refracts, it diffracts, just like all waves do. But light also has particle properties. Specifically, it has a given amount of energy, and, as was found in 1923, it has a given amount of momentum as well. In fact, Einstein borrowed a word from the study of electricity and used the term quanta, which is plural for quantum, to describe the bundles of light energy. By the way, we have a modern word that represents light as a particle, the photon. The idea that light has both wave properties and particle properties is called the wave-particle duality of light. Previously, it was thought that something could be either a particle or a wave, but not both. The modern understanding of light argues that this isn't the case. Something, in this case light, can have both particle properties and wave properties at the same time. This shift in viewpoint would also have dramatic effects in our understanding of the nature of matter in the mid-1920s. There are some important implications of Einstein's idea that the energy of light is related to its frequency that we experience in our everyday lives. Visible light, the light we see, consists of light between frequencies of 1,000 trillion waves per second and about 500 trillion waves per second. Blue light, the light that's about 1,000 trillion waves per second, has the highest energy, while red light, on the other end of the spectrum, has the lowest energy. The reason we actually see visible light is because this light has enough energy to cause some chemical reactions in our eyes that send signals to our brains. A photon of visible light causes a molecule called the retinal in the backs of our eyes to rotate around a single chemical bond. This rotation is the start of a series of chemical reactions that ultimately sends an electrical signal to the brain. Another series of chemical reactions regenerates the original retinal molecule, getting it ready for another cycle. Generally, these cycles work well, but if too much light enters our eyes at once, we have difficulty seeing clearly until the chemical reactions regenerate the retinal. Surely most of us have experienced the temporary blindness, the spots before our eyes caused by too much light all at once. This also explains one of the dangers of lasers. If a person were to look at a laser beam, the intense light would overwhelm the chemicals in the retina, and the person might be temporarily blinded. But the light we see isn't the only type of light there is. There's light we can't see, too. Going to lower frequencies, lower energies, we have infrared light, then microwaves, then radio waves. These types of light have lower energies than visible light, and because they don't have enough energy to stimulate the retinal molecules, we can't see them. But we still use them. Think about microwave ovens and the radios in your car or your cell phone. These low-energy forms of light can be detected by electronic circuits, but their interactions with matter are very different and much lower in energy than the interactions of matter with visible light. Going in the other direction, however, there are higher energy types of light, ultraviolet light, X-rays, and gamma rays. These types of light can interact with matter too, but not just by twisting chemical bonds around. Instead, they have enough energy to completely break chemical bonds, which is usually not good for our health. So we have to be careful exposing ourselves to them. For example, doctors strongly recommend sunblock for people spending time outdoors in the sun, even in winter. Why? Because sunlight contains a little bit of ultraviolet light, which has enough energy to break some chemical bonds in your skin, causing long-term damage, including cancer. Many people admire or even cultivate the well-tanned look, but that same light causing that look may also be causing skin cancer. Many doctors, nurses, and even patients wear protective clothing around X-ray machines because these X-rays have a lot of energy, and too much exposure can cause cell damage. And gamma rays are one product of nuclear energy, so workers in these fields need to protect themselves as well. The entire range of light, radio waves, microwaves, infrared light, visible light, ultraviolet X-rays, and gamma rays, are collectively called the electromagnetic spectrum. They are all forms of light, but with varying wavelength and frequency, and, as we now know, energy. The values of these three characteristics vary smoothly, so one can say that these properties are continuous, like a ramp. But for any given wavelength, for any given frequency, the energy of that wave of light, that photon, is specific. It cannot be different. It comes in a fixed amount. So at its most fundamental level, energy is discrete. Energy is a staircase, not a ramp. The fact that energy is discrete was going to have a major impact on science as it developed in the early 20th century. Planck's proposal that energy is related to frequency, a proposal ultimately proven correct, is such a watershed idea in the development of science that physical science before 1900 is called classical physics, while the development of science after quantized energy is called modern physics. Planck's proposal and Einstein's application of it to light became a new theory and started a revolution in our understanding of matter and energy that continues to resonate today and, as we'll see, has a major impact on the nature of matter. Thank you.